Welcome to Data Skeptic, a podcast exploring the methods, use cases, and consequences of recommender systems. Welcome to another installment of Data Skeptic Recommender Systems. You know, recommender systems are everywhere. They power all your social media feeds, news sites, and probably other places you aren't even considering. Most of us think of our interactions with these platforms as like a personal, independent thing. It's you and the website you're sharing your preferences to. And ideally, they're good stewards of that data and produce you good recommendations. But today's guest studies what happens when those assumptions break down. Kat is a PhD student at MIT studying strategic learning. She joins us to discuss her research on how users can collectively and intentionally manipulate recommender algorithms, and why, perhaps surprisingly, that manipulation might actually benefit the platforms that are being manipulated. We'll discuss how game theory and matrix completion play a role in her model, and also get into some interesting survey data that suggests this kind of coordinated algorithmic activism is more common than you might think.
So my name is Ekaterina Filadova. Usually I go by Kat. I'm a PhD student at MIT EECS, and I study strategic learning. In my PhD, I focus on basically machine learning, or more broadly, AI in settings where the data you're learning from is strategic. So if you make assumptions that say, like, the data is consistently coming from a single, data generation process, like a single distribution, or something like that, or you assume that the data is IID, so independently and identically distributed, you can make a lot nicer, cleaner theoretical statements about what your learning algorithm is going to do and what happens in the worst case and things like that. Sometimes there are also similar guarantees for if your data is adversarial. So if it could be potentially really bad, but there's this in-between case where basically your data might be strategically manipulated, but it can't be manipulated entirely, so it's completely meaningless. So our classic example of this is loan approval algorithms. If I, as a bank, wanted to have an algorithm that approves people's loans, and I put some sort of amount of weight of my algorithm on how many credit cards you have, people could kind of strategically take out more and more credit cards, and it doesn't really improve their quality or their qualification for a loan, probably, but it does get them more approved in the algorithm. So I think about these kinds of algorithms in sort of robustness ways and fairness ways and lots of different theoretical kind of ways of what happens when people are strategic in this kind of way, and how this idea of how the algorithm functions. In recommender systems, this is really applicable. There's a lot of strategic action that happens on those kinds of platforms because people have a pretty elaborate idea of how they work. A lot of human-computer interaction literature studies this. And since they have a good idea of how they work, or at least a heuristic one, they take advantage of these kinds of how do they work ideas and behave strategically on the algorithm. So for my kind of work, there's a lot of interesting questions to ask about how Rex's algorithms specifically function, because I think a lot about these more general strategic ideas.
On the surface, it seems like recommender systems might not be at risk of this strategic manipulation. It feels very independent and identically distributed. I'm in my living room and someone else is in their living room, and I'm not necessarily calling them and say, thumbs up this show or this video or whatever. Where does the possibility of manipulation come in?
Well, so first of all, to use YouTube as an example, definitely a lot of people end their videos and say hey, subscribe to my channel, make comments or whatever, which is sort of a baseline, I guess. But even further, I think in the recent years, where people have more and more idea of how the YouTube algorithm works, people will say for the algorithm, I want to make my show, pop out in the algorithm, subscribe, comment, support me. There's some human-computer interaction work, so some behavioral focused, human-centered work that documents people doing things oh, I believe the algorithm is spreading misinformation, so I purposefully don't interact with this kind of content, or I believe this content is bad for XYZ reason, and so I purposefully don't spread it, or the opposite. People see things oh, this person is promoting their GoFundMe or things like that, and so I'm purposefully going to push it out. I think it's unclear to me whether those kinds of actions are create broad, huge boosts of the content. But I think what's more interesting, what we ended up exploring in the paper, is that those kinds of actions also end up being formed on a sort of larger scale. So people take on these strategic movements where they say hey, we believe that this kind of content is suppressed, and collectively kind of try to push it out. Even if it were not effective on a algorithmic scale, like in terms of like it doesn't affect the algorithm, it definitely affects societal trends and like discussion about this. So whether it's effective or not, because it happens and because it seems to be potentially incentivized to happen because people think it will be effective, I guess it could be high stakes or low stakes, but it's definitely something that seems to happen on a human level.
What first got you interested in recommender systems?
So I was always interested in this kind of, the broader topic is something called algorithmic game theory. And I was always interested in how inter-user, user algorithm creator incentives align or potentially affect each other. So how people might be incentivized to like resist an algorithm, or how people might be incentivized to pretend to be something else to get classified positively by the algorithm. So I always found those kinds of things interesting. And from a like societal, cultural kind of side, I spend a lot of time consuming content on YouTube or TikTok or Instagram or whatever else. And I thought it was very interesting how many like human dynamics were going on there. I guess from a marketing perspective, you think about this as like, how do you keyword take advantage of the algorithm to like, what things do you use in the title to make sure the content is pushed out by the algorithm, et cetera, et cetera. And I thought it was really interesting from like an algorithmic design and algorithmic study perspective that this happens for humans. So like on the technical side, you know, we might think about designing these Rexis algorithms with various downstream effects, and like it ends up incentivizing certain like titles that are maybe more catchy than others. But I found it really interesting that humans notice these things and develop these whole pretty elaborate folk theories is the word that's usually used here. Ideas about how the algorithm works and how to take advantage of it and stuff like that. And so I was very interested in that from a societal perspective, and I was really interested in the like game theory math aspect. And so it felt very natural to think about this in the context of like game theoretic analysis of Rexis.
I don't know that that's going to be an obvious insight to everyone. Could you talk about how we frame a recommender system as a game?
In the past couple of years, people in like theory land got interested in this idea of like, okay, the recommender system algorithm very crudely works in this way where you have a recommender and you have like a user, and the user interacts with content. So, you know, videos or posts or whatever else, but we can abstract it and we say it just interacts with some items. And interacts being here like maybe views, likes, comments. So again, like in the actual Rexis applied world, all these things are much more complicated, and you have to think about how to convert these things into numbers and like all this interesting, like non-trivial stuff. But in theory land, we might think about it as just like some interaction. This interaction is a number. We're going to hide under the rug, like exactly how we get to that number. But okay, like in this baseline idea, the user and the algorithm are like the two players here. And so we think about this as a two-player game. And we say, okay, the recommender maybe wants to provide the items that the user is going to engage with the most. This is a pretty common assumption that we make, because on engagements, you can sell like advertisements and stuff like that. But the user maybe wants to make sure that like they get the kind of content that they want, and maybe they don't trust the algorithm to be perfect, or maybe they think the algorithm is like a little bit slow to update or whatever else. Like they might have various theories about how the algorithm functions, and for whatever reason, it's not perfectly aligned with what the user wants. And so the user might not interact with content in a way that's just like, I'm personally interested in this content, and so I'm just going to view it the exact amount that I just want to watch the video for. People end up being a little bit more complex in their interactions with the algorithm and think, okay, even though I might not otherwise like this video, or I might not otherwise click this video to add it to my history right now, I will just to make sure in the future it gets recommended to me. But the point is, there's a strategic process that the user is going through that's not purely just, I'm going to interact with this because I want to see it in the moment. Because these complex processes are happening on the user side, it becomes worthwhile and interesting to analyze it from a two-player game perspective. You want to have an understanding on basic general theoretical guarantees that the algorithm will have after interacting with such a user. Because normally you might imagine with simpler thought processes happening for the user, it's kind of easier to think about what happens. Like in the end, we hope, okay, the algorithm learns what the user wants and just gives that all the time. But if what the user is doing something more complicated, we don't necessarily want to make those guarantees without understanding it better. And so that literature came out like a few years ago. There's two key papers, one from my advisor, Hara Padamata, and another from a friend of mine named Sarah Sen, that analyze this two-player game version. But this is then still sort of like less complex than what happens in real life. I mean, all this is less complex than what happens in real life because this is, a game theoretic model. But it's still a step away from what we wanted to say about real life in our paper, which is that in this two-player game, you can analyze the user's thought processes that relate to themselves. So if I'm the user and I want to make sure I see some niche content again in the future and I interact with it more now than I would otherwise, we can think about that in the two-player game, and that's great. But real recommender systems are often based on this like collaborative filtering idea. So the idea that like, hey, the recommender can learn something from the fact that if I am very similar to you and I like some content, probably you'll also like it. And so these kinds of like inter-user, inter-item dynamics are important in a real recommender system. Maybe depending on the algorithm, but like in general, like you can get some juice out of these kinds of connections. But the two-player game can't account for this because you're thinking about just one recommender and one user. And you can account for lots of interesting game theory dynamics, but not this like collaborative filtering idea. And so we wanted to consider a multi-agent game in the world of in the like vocab of game theory that would be able to account for strategies where a user's strategy about whether I interact with the content right now is dependent not just on what I personally want, but maybe how I want to influence other people's recommendations. And so hence the multi-agent game, and hence why we want to think about guarantees in this context. And again, like I think I've talked to some people before who find it maybe unbelievable that this kind of multi-agent thought process happens between even like pretty normal users, because it's a little bit of a chronically online thing to do. But there's a lot of human-computer interaction literature that talks about how and why this happens. And I can talk about it more if that's interesting.
I definitely want to unpack the multi-agent game, but before we jump right in, could I ask you one more thing about the two-player game? In a game theoretic model, usually we talk about an equilibrium. There's a pair of strategies where no player is incentivized to leave their strategy. How does that play out in the existing literature that focuses only on the two-player game?
From a game theory perspective, like equilibrium analysis is a pretty classic thing to analyze here. Both papers that I referenced a second ago, again, from Hara Padamata and from Sarah Sen, both of those analyze in equilibrium. In particular, like they analyze either in equilibrium or like how long it takes to get to an equilibrium they're talking about. And usually this equilibrium would be something like, I guess in human words, the equilibrium here would be something like the kind of fixed point of like at which point the learner has like learned all they're going to learn and starts providing consistent recommendations to the user. Usually in this kind of game theoretic world, we're imagining that users have static preferences, which is not exactly true. There's lots of interesting Rexis literature that assumes users, evolve their preferences based on what you recommend them. That gets much more complicated. The paper from my advisor, Hara, that one talks about how users who are maybe in like niche groups of interest get stereotyped into having to interact a lot with the thing that they actually want to see to be able to get it. And so this is a stereotyping idea. But there's kind of lots of different things you could say depending on the strategic behavior you want to analyze. And the Sarah Sen paper I referenced analyzes these equilibria with this idea that like it happens because users don't trust the algorithm to serve them the kinds of content that they want or maybe will happily engage with.
There's the famous quote I'm sure you've heard, all models are wrong, but some are useful. So a two-player game, I'm sure there are a lot of good insights that come out of that. But as you point out, we sort of know the recommender system is doing some version of collaborative filtering. So it rather is an implicit multi-agent game here. Could you talk about the setup? Who are the agents in your model?
The key idea is that collaborative filtering uses the similarity between users and also items in order to give these recommendations. And so like the classic example would be like what I said earlier, I like something, you like something. If I interact with it, probably you'll interact with it somewhat similarly. So in the multi-agent version, we want to think about a case in which there are a bunch of users, and maybe a common way to think about this would be like a bunch of users who are each like vectors in an embedded latent space. I'm a vector in like d-dimensional space and you're a vector in d-dimensional space. And by similar here, this would be like in distance, our vectors are not too far away compared to two other people. And then like there's the recommender who's kind of like its own entity. And so then the idea would be something like, okay, maybe if you and I had similar embedding vectors and I knew this and I was like, this is just an example, like a malicious bad actor, and I wanted to make sure you got a piece of content that for whatever reason like is bad, but I wanted to make sure you got it because I was mischievous. Maybe like I would purposefully interact with that content, and I would hope that the recommender would pick up on this and like give you that content because I seem to positively interact with it and you and I are similar. This is actually not the strategic aspect that we ended up studying in the paper, but this dynamic is what's missing in the two-player game, or an example of it. And so in the multi-agent game, the players are the users, like the human users of the recommender system. And then there's like a principal, often we'd use this word, a principal or a learner who is the recommender. And then I can get into like our whole abstraction, because it turns out multi-agent games are really difficult. Two-player ones are already kind of difficult. If you know anything about like getting to equilibrium and stuff, all of that is difficult, but like multi-agent games are even more complicated. So we basically from there take a recommender system and like abstract it into a simpler multi-agent game.
Could we zoom in on the difficulty? Is it computational, or what are the challenges?
In our model, I've alluded to this a few times, we were interested in analyzing that in real life, there's this phenomenon where people believe, or maybe it actually is true, that the algorithm suppresses certain types of content that is sometimes like minority content. You know, this could happen perfectly naturally if the content is just not very popular. And so it's hard to like learn who likes it. It's hard to learn where it should be promoted. And so it just like doesn't get promoted very often. This is like a reason this could happen non-maliciously. Some people believe it happens maliciously. That's sort of not super important for the point that I'm going to make. But people have this idea that like, this content is suppressed. And so in real life, like people form these movements and they say like, hey, I think that these types of users or this type of content or what have you is underrepresented in what is promoted by the algorithm. Let's purposefully interact with this type of content. So interact being like, let's purposefully like, comment on, view this content to make sure it gets more promoted kind of fairly, more equitably in the algorithm. A lot of this happens on TikTok or Instagram. You can even see people like commenting the word boost to like boost in the algorithms. And so we wanted to kind of think about this phenomenon and what this would mean for what content ends up on the platform as a whole. Like this is kind of this equilibrium idea, although we didn't explicitly talk about equilibrium in the paper. But kind of like, what does the like set point end up being for the system? What does the algorithm end up being able to learn in this kind of context and all that kind of stuff? In that case, the thing that made it difficult is that we wanted to be able to think about how these users' strategies being like their interaction patterns with content, would affect each other. And like, if I made a choice, what choice should someone else make? And like in the multi-agent version, especially if people went like one at a time, like first I interacted and then you interacted and the next person interacted and maybe I interacted again, the process of like what my strategy means for you and the next person becomes much more complicated, because you can imagine there's like a bunch of users. In a two-player game, it's just me and the learner, and then it just kind of goes forward. And there is a difficulty of like multi-step analysis, but in the multi-agent world, there's also multi-step and like strategic like propagation from me to the next person. And so that was really difficult to analyze in a realistic sense, because again, like in a realistic sense, you know, agents don't interact at the same time. They interact over like different rounds. Like maybe I interact one day, you interact like an hour later and the next day, and et cetera. So those are the kinds of things that we need to simplify in terms of reasonable analysis of the multi-agent game.
Well, where is there room for user altruism? Or maybe what's your definition of user altruism occurring in a recommender system?
In the final version of the paper, we're currently in submission to a conference. In this version of the paper, we've kind of moved away from the idea of calling user altruism for a reason I'll discuss in a second, but it's perfectly reasonable. So the altruism that I was talking about in the current version of the archive paper that's up right now, and the word that I still use sometimes, it's the exact human phenomenon that I was talking about a second ago, which is that users have an idea about how much content may or may not be promoted on the platform. And a lot of times this leads to beliefs, or again, it could also be like perfectly true that some content is less promoted than other content on the platform. And in particular, what this means is then that like some users who like the content that's less promoted don't get this content necessarily because it's less promoted. Or likewise, maybe like a new user joins the platform and is not given this, niche kind of content because there's not much learned about that user. And so maybe the assumption that like they want popular content, that kind of thing. And so we call it in the current version of the paper altruism because the idea is there's a sort of collective of users who want to make sure the minority content, so the content that's like less promoted, the less common content on the platform gets shown to the users who actually would want to see it, which is something often human users believe doesn't actually happen, or maybe again, like truly doesn't happen. So yeah, the altruism here is sort of like altruism from a classic econ definition, which is to say, in my utility function, I value other people's utility as well. And so I'm altruistic because I want to make sure that like I am happy and also to some amount other people are also happy and that makes me happier. Does that make sense?
I think so, yeah. Or maybe I'm seeing it in three possible ways. You can tell me kind of which fits. There's one version where, I have a few friends that are content creators that don't have a huge platform, and it's like, I like everything, even if I don't watch it, because that's my buddy from high school, right? I want to promote him. There's maybe a more coordinated version, like being on the street team for a band, and you get an email, hey, everybody, let's go like this post. We're trying to get more views on our favorite band. And then there's like this, maybe I'm a niche user, or I'm not a niche user, but I'm aware there are communities that are underrepresented. If I'm just know about it, I'll give them a like or a watch or whatever it is to help put more light on something that should have more light. Do any of those mesh with your perspective on it?
This is really exactly why we wanted to change some of the vocab that we use for this in the final version, which by the time this podcast is out, it'll already be the version that's on archive. So it's good timing for that. But basically, yeah, so all those things are definitionally in the way we talk about it in the paper, altruism, because the idea is that all the humans who you just mentioned, the utility function, I use this term loosely. I think real humans don't necessarily have a utility function in their heads that they use to determine exactly what they're going to do in every moment. But the idea is I'm happier if my buddy who has this YouTube channel or podcast or whatever gets more views, and so I want to make it a little bit more popular. Or likewise, I care that these other groups are maybe underrepresented and not getting the content they want, so I'm going to put a little bit of energy into putting a like or a comment or whatever on this content that they would want to see, just to hopefully get it to them. All those things are altruism by this utility kind of definition. And the thing that we specifically focus on in the paper is what happens when there's a coordinated movement of a bunch of people who get together and say, hey, we're all altruistic to some degree here, so let's all get together and as a group push the thing that push this idea of helping the suppressed users on the suppressed items and content on this algorithm be a little bit more correctly recommended. That's kind of the idea. And the idea of what that happens in real life to some extent. In the paper, we reference a few examples of this happening, but also I think it's kind of a more realistic view on imagining these kinds of things are effective. I think if a random person does a very specific act of liking or commenting or whatever, it feels natural to assume that it's a drop in the bucket in terms of any real effect happening. So that's why we focus on this. I guess again, you could call it collective altruism, because it's a bunch of people who all have this shared idea of hey, we want to help this group that's not getting the kind of content that they want. And so together we're going to interact with the content in a strategic way.
What would surprise me to think a recommender system as a game would be zero sum. It's not that the platform wins and the user loses. The platform is trying to give the user what they want. So how does a group get their content suppressed in the first place?
First of all, I guess I'll say There are lots of reasons it could be suppressed. And I say suppressed with a lot of nuance because it sort of depends on like your definition and how strongly suppressed is used here.
Well, there's the term shadow banned. We're not talking about that, right?
Yeah, okay. Yeah, that's a good point. So like in the real world, like there are lots of these kinds of terms about what it means for something to not get shown to people and etc. So yeah, suppressed here could mean a lot of things. I guess I'll first say with zero-sum games. So when you get zero-sum games, it's because the utility of one player and the utility of another player are exact opposite of each other. So like I'm only going to be happy if you are inherently unhappy. And so that creates a zero-sum game because basically only like one person can win. And it's zero-sum because like I have +5 and you have -5 in terms of like our final utility. In a recommender system, it can be kind of difficult because what users want and what the recommender wants, whether they're aligned or not, I think depends on the specific platform and the specific platform's values and what they want to do and what the users on that platform want. And also depends on your perspective as like an outside observer, because you can assign your own like, do you think it's correct what the users want or what the platform wants? But basically, let's say like a very simple example of like this idea of suppression is kind of what we have in the paper. What we like the type of suppression that happens in our paper is the one that's maybe some people would call like the least malicious. A learner, a recommender system, can only learn preferences to a certain degree. Because it takes a long time to learn everything perfectly, and it's quite difficult, often it might be impossible, I can only learn so much. In our model, we have a specific example of like why you can only learn so much and what happens here. But like in a broad, high-level aspect, like, in general, you just can't expect something to learn everything perfectly. Like there's going to be errors. Some people might be like very underrepresented in the system. And so it's very hard to learn what they actually want because basically like you can imagine that, say I'm a recommender and I'm like randomly exploring, showing people various items. And then at some point I will have learned enough. I'll decide that I've learned enough. And then I will start recommending people things that I believe that they'll actually want. And so in this view, right, like imagine you have users who appear very, very infrequently in the system and they have like very niche desires. If I were to just randomly give people content to like test the space and to see how much people like things and how much people want them, I have to randomly give these very specific users a very specific item to see like, oh, they like this thing. And if I'm just purely randomly testing item and user pairs, this is not very likely to happen. And so the idea would be that like, because these users are not very dominant in the system and they like things that are a little bit niche, the likelihood of me learning this thing, if I'm doing it purely randomly, like there are ways you can get around this in the real world, but like in this kind of like silly case, you're going to have a harder time learning these minority preferences, minority preferences being what we call them in the paper. Minority, like just purely mathematically. And so the idea is like in this world, because I don't know what to recommend them very well, or either I just haven't been able to learn it, it would be much harder to learn. I end up giving them items that are more popular to people whose preferences I know, or to people that I can compare them to, who maybe they're like somewhat similar to, but not really. And so they don't really get the things that they want the most because they're just harder to learn. And so this is the kind of example we use in the paper. I will say there's human interaction studies of users and their views of recommender systems who believe things that are like generally more malicious. So, some recommender systems could be actually malicious and maybe want to push a particular narrative, or, maybe want to push things that specific users don't like. There are other reasons that content could be basically not served. Similarly, for example, like some recommender systems have safety protocols where certain content is suppressed for reasons that maybe it's like dangerous. That also could be the case. So there are various reasons, but the reason that we focus on in the paper is this idea of like, it's just hard to learn perfectly. And if something is not very prevalent in the system, it's probably going to be even more difficult to learn.
Well, I know every recommender system is a little unique, probably between what Netflix and Spotify and 10,000 other places have done, and they're all probably black boxes. What's the ideal way to model a recommender system for your research?
It's difficult to model because they're all quite different and they're black boxes and things like that. So the thing that from a game theoretic analysis point of view that we kind of went for is twofold, I guess. We started with a classic learning problem that represents recommender systems and then went from there. And then on top of that, do some like empirical validity things to see if like the theory, the model that we have is like obviously not perfect to real life, but does the result that we get from the theory match kind of what happens in a more realistic version? And if yes, then we're happy. And hopefully the theory is, again, like not perfectly one-to-one with what happens in real life, but like indicative of something that happens in real life and hopefully similar to why and how it happens in real life. So in our case, the first step that I said, which was starting from a learning problem, which is that at this point, a little bit older, classic, traditional way of thinking about recommender systems, which are now maybe like even more complicated deep learning things. But like a classic way you might think of this is like a matrix completion problem. And so matrix completion, you think about, you have a big matrix. The matrix is M by N. So M, the number of rows, are like the number of users you have, which again, like is probably a really big number. And N is the number of items, or maybe types of items. You could think categories of items that you have, which again is a really big number, and these are columns. And so this is a matrix. The matrix represents like the ratings or how much a user and an item match. So like how much me as a user in row M likes the item in column N. Ideally, you would want to know this whole matrix perfectly. And if I knew that, then I just give people the highest numbers that are in the matrix, and it's like big number, yay. But that doesn't happen very realistically, because in this like matrix completion problem, how you normally would think about this is like, you start out with an empty matrix, you being the recommender, and you want to know some of the entries in there. You don't know very much about it. You don't know how it's structured, beyond the fact that like users and items are probably to some degree similar to each other. So you know that it's going to be low rank, but that's all you know. You don't know what the entries are. And so you just start randomly checking like different user and item pairs. And so what that looks like in real life would be like, I'm a recommender. I give user Kat this item. I give user Kyle this item. And then I keep trying different things until it's a sort of like reasonable point where I think, okay, there are not that many ways the matrix could be completed. I feel pretty confident in like what items I think people like, what items people are happy with. And so I'm going to stop my exploration and I'm going to complete the rest of the matrix. I'm going to estimate all the other entries. And then I'm going to use that matrix to recommend people things. And so that's like the matrix completion problem. The question though, in the online matrix completion problem that I've just described, where like you're checking things round by round, is when do you stop? Because if you go for M by N rounds, then you've completed every single entry in the matrix. And again, you could do this, I guess, but M and N are going to be very large numbers. And if you do this, people probably don't want to stick around in the system for that long to like show their preference for every single thing. That's like not the point of a recommender system. So you have to stop at some point, and also you have to complete the matrix somehow. The way that matrix completion answers this problem is that you might stop at a point where basically like the high level, you're like confident enough that you've learned the system well enough, basically. And how do you complete the matrix? Well, because you assume the matrix is low rank, which basically just means that like users and items, there's like similarity between them. So there are some users who exist who are like slightly different versions of other users, or some users are like similar to two other users combined, those kinds of things. So low rank being like the number of independent rows, linearly independent rows or columns is smaller than the number of actual rows and columns. And so because you assume it's low rank, you complete it by solving a optimization problem where you fix all the entries that you know. These are like the user item pairs you already queried. And you complete the rest of the elements such that you get the lowest rank possible matrix. This turns out to be a hard problem. It's actually NP hard. So real recommenders who are using matrix completion would get around this in sort of other convex relaxation ways. There's a old, at this point, Netflix recommendation prize that talks about matrix completion, where people talk about how to do this efficiently and like approximately. But yeah, that's like the matrix completion, collaborative filtering problem, and that's what we use as the foundation for our model. I guess the important thing to note is that matrix completion is clearly collaborative filtering, because as I said, like, you complete the matrix partially, and then you fill in the rest of the elements using a rank minimization problem. And that inherently takes into account what other people's elements are, because you're trying to fill in elements such that the linear independence between different rows and columns is like minimized. So it's a collaborative filtering method, but it's not necessarily one that everyone uses, right? In fact, I think these days a lot of the black box algorithms are probably this like complex deep learning thing. Honestly, you could even be like lazy and say, I'm going to fine tune an LLM to be my recommender system and just hope that it has like the knowledge that you want it to have. And so in real life, the matrix completion thing is a little bit old. And so we have our model that's like built upon that idea. And then we have an experiment. Unfortunately, the experiment that you've read is in the older version of our paper, but we'll be posting a newer version of the paper, which has this newer experiment, which is that basically we do this fine-tuning LLM thing that I just mentioned, which again, like, is a silly thing to do. You wouldn't want to do that in real life. But the idea is like, the LLM is like a deep learning system that if you are like being a little bit lazy with creating a recommender system, or, you're kind of hoping to take advantage of a black box that you don't want to train yourself, you might take this LLM and fine-tune it to be your recommender system. And so what we've done in our experiment is basically say, we're going to take an LLM, fine-tune it to be a recommender system, and then see how it recommends. And then we're going to say, okay, we have people who are doing this collective altruistic action on the data, and then fine-tune a new LLM recommender system on this like collective action, strategic data, and see how the two recommenders compare. And it turns out that they mostly support our theory, which is that the collective action, at least to varying degrees, is effective in getting the minority users or the less represented users in the system the thing that they want to see. So that's the two steps. Sorry, maybe I should have separated them a little bit, but those are the two steps. The first step being, how do we do the model? Like, how do we know that the model is reasonably good? How do we set up the model? That's like based on matrix completion. And the second one is, how do we think about it being like reasonably good? That's in our empirical validation.
Well, if I were thinking about contributing to a collective altruistic action, I've got two questions on my mind. I'll ask you in sequence. The first is my participation going to hurt the recommendations I get today?
So in our theory, the punchy thing, at least to people who are other theorists who would see this and be like, oh, wow, that's interesting, is that we see what we call like a Pareto improvement, which is to say we study sufficient conditions such that there's a Pareto improvement in recommendation. What that means is we specifically try to find the mathematical conditions under which people who are in the collective who participate according to the rules that like you set for the collective help other people but don't hurt themselves at all. And hurt themselves being like, we assume that there's like no cost to adding a like to something. There actually in real life could be, maybe it's like a reputational thing, or like it takes time to find things to like, or it takes time to like write the comment. Ignoring that, you could still like accidentally hurt your future recommendations. In the theory, we end up finding these sufficient conditions such that you can like avoid doing that. In real life, though, that's not necessarily the case, and it's like hard to know, like, if I like this thing, maybe I'll get it in the future, or how much will I get in the future? Because I'm okay with a little bit, right? But like not too much. I don't want my whole feed to be inundated with this thing that I want to help with. That's difficult, and like our theory can't yet perfectly answer this, honestly, in large part because at that point you get to, at least in my opinion, like a point where exactly what recommender system you're using matters a lot, like exactly how the black box functions. Because honestly, like depending on how your recommender system works, like you could be very or very not sensitive to this kind of thing. People complain about different recommender systems platforms being too sensitive or not sensitive enough to like how much I interact with something today, for example. So I think the theory is not great for this kind of question, because it's better for like this high level, like, is it possible to be effective question? In our empirical validation, the LLM experiment that we do, in that experiment, we end up being able to see that the test accuracy doesn't go down very much. So the minority users are helped, but accuracy is okay. And this is primarily because like in some recommender systems, you would see like so many users who like the popular items, and the popular items are so popular that even if you like or try to help this kind of collective a little bit, the popular stuff for you still dominates so much that like it doesn't hurt that much, but it's definitely not going to be the case everywhere. So I think that to answer this question, more specific experiment and empirical work could be done.
Well, and my other question then, when considering should I participate in this collective altruistic action is it going to be effective? Is this worth my time? What do your simulations show?
The simulations that we have so far show that it definitely can be effective. And in fact, I mean, like, the simulations show that they can be effective. The simulations that we have, to briefly describe them, are again this like LLM thing. In particular, what it looks like is an LLM experiment on a bunch of data from Goodreads. Goodreads is a platform in which people can interact with books, so they can add a book to their shelf to indicate like they're interested in it. They can review a book, they can rate a book out of 5, and they can like mark a book as read. And so there's this data set that we use, and we say, and we fine tune an LLM to basically say, hey, this is the user's past profile of previous interactions with a bunch of books. Based on this user's profile of interactions, can you recommend to this user a book they should add to their shelf from this next year? It depends, I guess, on how familiar you or the listener are, but basically, like, the books that we use for this are all YA, young adult genre books. And there are sort of in every year, like, some very huge behemoth, like, popular books. And so as a recommender, like as the LLM, it can get pretty high accuracy by, for the most part, when it's unsure, recommending the most popular books. And so, like, in this world, the recommender ends up being quite similar to the one that we talk about in the paper, which is that, like, there are some very, very popular items that are just, like, safe recommendations to the basic user if you don't know. And then we say, okay, what if instead the data were slightly different, such that people who liked the popular thing cared about making sure, to some extent, these, like, authors who are less interacted with get some level of promotion. Like, they just want to make it a little bit more equitable. Because the thing that we see in the baseline is actually that, like, a lot of the authors that do have some people who want their books, like, actually it gets recommended almost never when compared to, like, a popular book. And so, you know, we say, like, what if there are some users who like the popular books, who want to make sure this is a little bit more equitable? And so they just, like, add to their history of shelves interactions with, like, previous books from these authors. Or they maybe sometimes add to their shelf one book from this author just to, like, try to even this out. And it turns out that, like, this can be effective in making sure that people who want the books from these semi-unpopular authors actually get them. In this world, it's effective. I'm inclined to say that, like, the reason why it becomes effective here is because there's this, like, huge popularity split between the unpopular items that are not getting recommended and the popular items. And this popularity split basically leads to this idea where it's like a safe bet to recommend the popular item. And so you kind of just want to fix this a little bit. I think that in these kinds of cases, when this is the driving factor of what's going on in terms of, like, algorithmic suppression, this works pretty well, the collective action. But there are definitely cases in which it might not, and when it might not be effective. So I think that the theory seems to point that it can be effective, and the empirical evidence that we have points that it can be effective. But there's definitely a lot of room for a lot more interesting empirical evidence here. And I kind of hope that the paper, once it's published in the sort of final venue, sparks some interest in people who are more seriously in, like, the real recommendation space in terms of, like, trying this kind of experimentation with, like, the actual black box algorithms that are happening. Because again, like, I don't have access to those, at least, you know, not at the moment. In the future, maybe. But there's a lot of interesting experimentation that I would love to happen at some point.
Well, it seems to me from reading your paper, there's a good reason to think collective action ideas like this can certainly be effective. And there's a lot of, we didn't go through the algebraic derivations, but there's a wealth of those in the paper that support it. And of course, your simulation. But to complement that, you also went out and did some survey work to see what actual real people think. Could you talk about that process and what you learned?
At this point, the survey is one of the early things that we did, really, to make sure we didn't want to start the paper and it be something that, like, no one does and no one cares about. The survey data, first of all, maybe I'll preface with, there's a lot of very interesting human-computer interaction work that this paper is inspired by, which I always plug because, like, I'm a big fan. I don't personally do it, but I'm a big fan of human-computer interaction work, and I think it's sort of unrecognized. it's disproportionately organized by computer scientists and computer science community sometimes. But like there's a lot of very interesting human-centered work that already talks about these phenomena happening and like talks about how users develop these theories of how the algorithms work and talks about like, do people do strategic stuff, et cetera, et cetera. But there wasn't very much work at the time of writing this paper that deeply analyzes the interpersonal strategies that users have. So again, these are the ones that like utilize the collaborative filtering aspect, the ones that say, oh, I know there's like this idea of people similar to me will get some stuff from me. So I want to make sure, like, I want to influence that a little bit. There's some very small amount of data that indicates people do this, which is what inspired the paper, but there's not a ton of work that asks about this question specifically. So that's what we wanted our survey to understand. We wanted to understand, do users actually understand that like how they interact with items can affect what other people get? Maybe not personally, but like in general, like overall, this group of users' interactions affect what other people get recommended. We wanted to know if people are aware of this idea, this, again, collaborative filtering, to use the actual vocab idea. And we wanted to know if people know about that, do they like use the knowledge to like do anything strategic? Overall, we ended up saying that it seems like yes. I fear I don't have the numbers in front of me, but a significant amount of people from our small survey of 100 understood that their own interactions have impact on the larger learning that's happening, of like learning of other people's preferences. So that, first of all, was like an interesting thing to see. You know, it's not a super new conclusion compared to some of the existing human-computer interaction works, but it's good to confirm. And then we see, I think it was 32 out of 100 people do some type of strategic interaction or lack thereof to try to influence other people's recommendations, which I thought was very interesting. To be honest, like I'm the one who like did this theoretical work. I was kind of surprised that 32 out of 100 was like pretty prevalent. Like it's less than half, right? But like if you have 100 people and 32 of them did some strategic thing, that's like not insignificant for sure. Especially like, you know, if you scale up the numbers and those get really quite big. So honestly, I was kind of surprised. Like I was pleasantly surprised because obviously, again, like I got the paper, so I wanted to see something. But yeah, so it's surprisingly prevalent. That's really the main conclusion. It's only 100 users of our survey. And actually, the 32 users I'm talking about purposefully interacted or avoided interaction with content to influence other people's recommendations. That's like the phrase that we have. I think that that's a definitely non-negligible amount of people. And I hope this is like in the future work of the paper that'll be an archive, that like basically there's a lot of human-computer interaction work that I hope can further analyze this idea, because it's still unclear what platforms this is actually most prevalent on. And it's honestly, it's still unknown, at least to me, what kinds of interactions are the ones that are the main collective action targets. So like, you know, I could say, oh, I'm going to like a bunch of things from these users that I care about, but I could also say I'm going to comment on their items, or I'm going to like share them with a link or whatever. And so there's also different interactions that actually could happen. And so those are still unclear which ones are the most popular. So yeah, there's definitely a lot of open questions on the human-computer interaction side.
So one thing recommender people face is a problem of like cyberbullying, that maybe a collective users go and all thumbs down some creators' content to de-promote it in some way. It's like a data poisoning attack, and they probably want to filter that out. If they're inclined to filter things and they're filter heavy, and they notice this sort of altruistic collective action, how would you encourage them maybe not to filter? What are some of the benefits of these actions in cases like the ones you've studied?
So first of all, again, the paper, if one were to read the actual, like if one were to go and read the paper after hearing this discussion, it would be clear that the thing that we focus on is specifically this like collective altruism thing of like, I want to help the minority users, so I'm going to purposefully interact with this thing. But like the broader strategic actions that we talk about are applicable to lots of malicious things as well. So like bots, bullying, mass negative reviewing, all these kinds of things. And so in some ways it's like unclear whether you want to try to get rid of this incentive to be collectively strategic, right? Like there's perhaps an incentive to like create a bunch of bots to like mass negative review things that you don't like, right? And the system might want to get rid of this incentive somehow. It seems very difficult, but like you might want to. The thing that we say in the paper basically is that in this case, because the strategic altruism that's happening is like not something that is entirely against the goal of the platform. So in particular, you might imagine a platform just wants to get people the thing that they like the most. Or in a more realistic way, like platform wants to give people the things that they like because it maximizes engagement, and you can sell ads on that kind of engagement. You can sell ads when people view a video. So because the collective action in this case is making sure that users who are otherwise underrepresented in the system actually get the content they want, it ends up being quite aligned with the platform, right? Like you end up happy because you're helping people that you care about in the system, but you also make the platform happy because the platform can sell ads on your, like your target, on your like strategic interaction. So like if I view a video that I don't necessarily want to see, but I want to make sure other people see it, while I'm viewing it, the platform can show me ads. So like that's good for the platform. And also, now the platform can give the underrepresented users the thing that they want, and they'll interact with it more, presumably, and then you can sell ads on that. So in some ways, this is like beneficial for the platform, but yeah, it's how to separate this kind of collective action from more negative ones that you probably want to disincentivize is a good question. It's not one that we focus on in the paper, so I don't have a great answer for you off the top of my head. But okay, I think maybe the way to think about this would be probably not through the theory lens, but to say that like there are probably behavioral patterns that could separate these things, like on the behavioral side of this collective action stuff. How people do collective action, it's not super well documented. Obviously, there are like news stories and some human-computer interaction papers that talk about this, but there's not a ton. But I would think that the way to separate them is in this kind of behavioral pattern way, which is of course like difficult because then like bots will pick up on this and then start to become more human-like. So there's always like this like difficulty in EECS, and I think it just falls into that same direction as a lot of other things do. But that's probably the best way that comes to my mind. But yeah, like I would say the interesting thing to me was that like upon thinking about it, we decided that actually this collective action thing, even though it's like people behaving falsely, right? Like it's me interacting with content in a way that I wouldn't personally be interested in. We found that like by some metrics, it helps the platform, right? Because it like improves recommendations. And also I'll say like on the human side, these kinds of movements are often like algorithmic protest movements. People are like trying to resist the algorithm because they view this person very negatively, right? Which again, I don't want to specifically say like it's definitely malicious or not malicious. It could be kind of either way on some platforms. And so like often the movements, the human version of the movements is like a protest. But, like at least game theoretically, it's a protest, but like it's a protest against the platform, but it helps the platform. So it's kind of an interesting note, I guess. Like it's in the same vein as like all press is good press, whether it's bad or good.
What's next for you?
Recommender system wise, I'm potentially working on some interesting stuff, actually in part about this, like what if users participate in collective actions too much? Like what happens? How do you think about this theory wise with a past guest of yours on the podcast, Rebecca Solganic. So some of this work will continue, I hope. I am hoping in talking about this paper more with some human-computer interaction empirical people that there's, like I said, there's so many empirical and human-computer interaction. There's also theory stuff to do in this paper. It's just that, like, I'm the one who did the theory stuff. So, like, to me, it's kind of like a natural next steps. But there are natural non-theory next steps that I'm not very well equipped to do. So I'm hoping to get people interested in these things. So if anyone listening is interested in them, they should reach out to me. But yeah, so hopefully some of those next steps. And, I have lots of my other game theoretic strategic learning work completely separate from Rexus that I will also continue to do.
And is there anywhere listeners can follow you online?
Sure, yes. So first of all, they should check out the paper, which is on Archive. And online, they can follow me on Twitter. My handle is my first name, but with an 8 instead of an A.
We'll have links to both in the show notes for listeners to follow up. Kat, thank you so much for taking the time to come on and share your work.
Yeah, thank you so much for having me.